Beneath 3,768 meters of Antarctic ice, in the center of East Antarctica sits a body of liquid water 250 kilometers long and 50 kilometers wide. It is sealed from the atmosphere by a continuous ice sheet that has been in place for, on the lower estimates, 15 million years. A Russian drilling team reached its surface in February of 2012, after 25 years of work. What they found is still being argued about. In the early 1970s, ice-penetrating radar surveys flown by the Scott Polar Research Institute over East Antarctica produced anomalous readings, a flat, smooth interface several kilometers below the surface, where the radar return looked nothing like the rock ice interface that should have been there. The British glaciologist Gordon de Quetteville-Robin, who led that program, suggested that the smoothness was consistent with a layer of liquid water trapped between the ice sheet and the bedrock. The interpretation was confirmed in stages over the following 2 decades. Soviet, then Russian, glaciologists working at the Vostok ice-coring station, itself in operation since 1957, combined their radar and seismic data with American satellite altimetry. By 1996, an international group led by Andrey, Kapitsa, Robin, and Martin Siegert published a map and a name for the body of water. Lake Vostok, the largest of what is now known to be a network of more than 400 subglacial lakes underneath the Antarctic ice sheet. Lake Vostok is, by surface area, comparable to Lake Ontario. Its volume, about 5,400 cubic kilometers, is comparable to Lake Michigan. The water sits under the weight of nearly 4 kilometers of ice, at a pressure of roughly 350 atmospheres. Under that pressure, the water remains liquid even though it is at a temperature only slightly below the normal freezing point of fresh water. The base of the ice above the lake is itself just slightly above the pressure melting point. Heat from the rock below the lake, the residual geothermal heat of Antarctica's ancient continental crust, keeps the system from freezing through. The water is, by all the modeling that has been done, oxygen-rich, but in an unusual way. Air bubbles trapped in the ice above the lake have been pressed into solution at the ice-water interface. This means the dissolved gas chemistry of the lake water is unlike any surface water on Earth. The oxygen concentration is, by some estimates, 50 times higher than in normal lake water. The lake has been continuously sealed from the atmosphere for at least 15 million years. On the most cautious published estimate, some published estimates go to 25 million years. An aquatic environment isolated from the surface for that long, under that pressure, in that gas regime, is one of the closest physical analogues on Earth to the suspected liquid water environments under the surface ice of Jupiter's moon Europa, Saturn's moon Enceladus, and the polar caps of Mars. NASA and the European Space Agency, planning instruments for outer solar system missions, used Lake Vostok in the late 1990s and early 2000s as their working terrestrial test environment. If life existed in Lake Vostok and could be detected through ice, the same techniques would, in principle, work on Europa. This raised an immediate problem. Any drilling that opened a connection between the surface and the lake would, on contact, contaminate a body of water that had been chemically isolated from the planet's surface for tens of millions of years. The first international scientific recommendation, made by an interagency group coordinated through the Scientific Committee on Antarctic Research in the late 1990s, was that drilling should not proceed without a sterile recovery protocol. The Russian Antarctic expedition had, by the 1980s, an ongoing ice-coring program at Vostok Station. The original purpose was paleoclimate research, recovering air bubbles trapped in ice over the last several glacial cycles. The drilling fluid in standard use, then and now, is a mixture of kerosene and freon. It keeps the borehole open and prevents it from collapsing under the pressure of the surrounding ice. It is also extremely contaminating. The Russian team's plan, as developed in the 1990s under the direction of the lead engineer Valery Lukin, was to drill through the ice using the standard kerosene fluid, but to stop several tens of meters above the lake surface, switch to a sterilized aqueous freezing fluid for the final approach, and let the lake water itself rise into the borehole and freeze, providing a clean sample. International commentary at the time was skeptical. Several papers in EOS and Nature through the late 1990s and the 2000s questioned whether the kerosene borehole approach could be adequately sterilized at the lake interface. The Russian team proceeded. Drilling continued, in stages, through the southern summers of the late 1990s, through a long pause for review, and resumed in the late 2000s. On the 5th of February 2012, at a borehole depth of 3,769.3 meters, the Russian team reported breakthrough. The borehole had reached the surface of the lake. Water from the lake rose into the bottom of the borehole and froze, as planned, providing a frozen sample column for later recovery. The borehole sample was recovered in the southern summer of 2012-13 and analyzed by Russian and American laboratories. The Russian team, in a paper published in Microbiology in 2013, reported the detection of bacterial DNA sequences not matching any known surface organism. An American team, working independently on parallel samples obtained from accreted ice that had frozen on at the bottom of the ice sheet from lake water, published in PLOS 1 in 2013 a detection of more than 3,000 microbial DNA sequences, with both bacterial and eukaryotic affinities. A subsequent re-examination by another international group raised contamination concerns. The drilling fluid had unavoidably entered the borehole. Distinguishing genuine lake organisms from drilling fluid contaminants was non-trivial. As of the most recent published reviews, the cautious scientific position is, there are signals consistent with novel microbial life in Lake Vostok water, and there are signals consistent with contamination, and the ratio of the two is not yet definitively settled. Whether the microbial signals from the 2012 and 2013 samples represent genuine lake biology, drilling fluid contamination, or some mixture of the two, the published positions differ. Cleaner sampling protocols are proposed. Cleaner samples have not yet been recovered. Whether the lake's geochemistry, in particular its high dissolved oxygen concentration, is uniformly the same throughout its volume, or whether the lake has internal stratification with very different conditions at depth. Modeling published since 2015 suggests stratification is likely. Direct measurement is not yet possible. Whether other large subglacial Antarctic lakes, particularly Lake Whillans, where an American team reached the lake in 2013 with a clean hot water drilling system, and Lake Ellsworth, where a British attempt in 2012 failed, represent similar or different chemical environments. Whillans samples did show clear evidence of resident microbial communities. The question of how the Whillans environment compares to Vostok is open. A flat radar return spotted in the 1970s, identified as a layer of liquid water in the 1990s, mapped and named in 1996, drilled toward for 25 years, and finally reached on a single day in February of 2012. The lake is still there. The water is still under nearly 4 kilometers of ice. The sample column is still being analyzed. The next clean sample, when it is taken, will probably come from a different borehole on a different lake with a hot water drill that does not leave kerosene in the hole. That work is still being planned. Antarctica has more than 400 subglacial lakes. Lake Vostok is the largest. It has been sealed since before there were modern apes on the African plains. The first time anyone touched its water, the year was 2012.